Dünya çapında en yaygın kullanılan veri bilimi platformlarından RapidMiner'ın kurucu ortağı Ralf Klinkenberg'ü yapay zeka ve makine öğreniminin sektörlere uygulamalarını anlatmak üzere sahneye davet ediyorum. Stage is yours, Ralf.
Hoş geldiniz. I'm sorry that my Turkish is not so good, so I'll have to give my presentation in English. Welcome to the conference and thank you for being here. Today I would like to discuss different industry applications of machine learning and artificial intelligence. And for that I would like to start with a simple presentation. How can I switch the slides? Thank you. So let's start with a very simple question. Can you predict the future? Who can predict the future? Okay, nobody. Let's assume we're at a reception. Everyone is holding a glass of water or champagne or some other drink. And then you see that one of your neighbors lets the glass slip. And the interesting thing is, if you look around yourself, the people around you, most of them will look a little bit shocked. Why? Because they predict that the glass is going to break when it hits the ground. And they predict that before the glass even hits the ground. How can they do that? Well, in the past, they have observed a lot of glasses fall when they grew up as kids. Maybe they dropped the glass every once in a while. And they learned. They learned that when glasses fall, they can break. And they learned certain patterns. For example, whether the glass breaks or not depends on how high does it fall, like from here or from there. How hard is the ground? Is it a hard stone floor? Is it a soft carpet? Also, how thick is the glass? Is it a very thin champagne glass? Maybe it's more likely to break. Is it a very thick water glass? Maybe it's more stable. So basically, from the experience, from the observations in the past, we have learned to predict when a glass is likely to break and when not. So basically, from the data of the past, we have generated a model of when glasses break and when they don't break. This is also called pattern recognition. And if machines do that, you can call that machine learning. You have data from the past, you try to find patterns to understand why certain things happen or don't happen, and then you also try to predict them. So there's different kinds of analytics when you talk about data analytics. The first type of analytics is trying to aggregate what has happened in the past, like how many items of type A did I sell in my store at location B. This is also called business intelligence. It's looking backwards. What has happened in the past to better understand. But then the next question is actually not only what has happened, but why has it happened? I want to explain things. And for these explanations, you can use diagnostic analysis or data mining. And then the next step is to predict what is going to happen next. Like which product is this particular customer most likely to buy next? Which customer is most likely to churn? Which machine is most likely to fail in my production line? There's a lot of questions where a prediction would actually create value if I knew the outcome of that prediction. So that's the next step, anticipating what's going to happen next or giving recommendation what to do best as a next step. And then the most valuable step is not only to understanding things or predicting things, but actually to taking action. To predict what's going to happen and how you should react to create the most value out of that prediction. And that's also called prescriptive analytics. So when we talk about machine learning, there's different types of machine learning. There's so-called supervised machine learning, where there is a teacher who can tell me what's right, what's wrong, or into which categories certain objects fall. For example, is this a machine that's going to be fine for the next 4 weeks? Or is this a machine that's very likely to fail within the next 2 days? So I can have different categories into which I want to categorize my objects. That's called classification. And there's a teacher that can give me these labels to tell me this was a case where it failed, this is a case where the glass broke, this is a case where the glass did not break. Then there's another type of supervised learning called regression, when my prediction is not a category but is a number. For example, how much longer is this machine going to work? Or in how many days is it going to break? That could be a prediction. Or how many pieces of this product will I sell next week? Typical cases of regression. Then there's also a type of learning called unsupervised learning, where you don't know a category or a label, but where you just try to organize the data, where you Try to find groups of similar cases as opposed to different cases. And that can, for example, be used also to find particular new groups of data that are relevant, or you have something called anomaly detection to find unusual cases in the data, which might, for example, be broken machines or which might be fraud cases in your transactions. This is just a very high-level view of different types of machine learning. What I really want to talk about is not so much the theory here, but more applications in the industry. What can you actually do with machine learning in the industry? I brought a few examples from our customer base. The first one is about demand forecasting. Predict how many products you are going to sell in a certain period of time at a certain location. Libri is one of the biggest book resellers in Europe. And they deliver to almost any bookstore in Europe, especially in Germany, where we have our home market. And the task here is to predict for every book title how often is it going to be sold the next day, the next week, the next month, for every location they serve. Because they give a guarantee to their customers, the bookstore. If a customer comes to the bookstore and the book that they want to buy is not in store, Libri guarantees that they will have the book the next morning, 9 a.m. To be able to give that guarantee, you have to very precisely predict how often each title is going to be asked for. And they have millions and millions of transactions every month. So this is a particular regression problem. How many books of a particular title do I need to have in store? Another example from the production industry, in this case the automotive industry, is called predictive maintenance. It's about predicting machine failures before they happen, so you can prevent the machines from failing. And this is done on the production machine level, like for example you can see the industry robots there, but it's also done on the level of the car itself. Why do you want to wait to take your car to the garage when the car fails? And then you have to have it towed or you have a problem. It's much better if the car already recognizes, I'm going to have an issue in, let's say, 2 weeks. Then they can already give you upfront notice, so you know early enough you can get an appointment at the garage and you don't need to wait until it actually fails. We do the same kind of applications in the aviation industry. Of course, for critical parts of airplanes like the turbines, obviously if they fail, the plane might crash. But also for much less critical parts, for example, like the coffee machines, the toilets, all kind of parts on the plane. Because if you're on a long distance flight, a failing coffee machine or a failing toilet is also something you don't want to have. We also do that in other industries, like the energy sector, for wind turbine components, or for the cement industry, for the machines that actually produce the base material for the cement that drill into the mountains. It can be used for all kinds of devices where I have data and, for example, sensor input, historical usage data, and so on, that allows me to come up with patterns to recognize when failures happen and try to predict them. That can be dealt with as a classification problem. For example, predict whether the machine is going to fail within 2 days or 2 weeks, yes or no. Or it can be treated as a regression problem, like in how many days do I expect this machine to fail. Here's another example of a use case from the steel industry. ArcelorMittal is the world's largest steel manufacturer. And they have the problem that sometimes in a very early stage of the production, when they first melt the steel and then they roll it in multiple steps to get, for example, the very thin pieces of steel that they can use in cars or planes, that sometimes the quality is not good enough for a car or for a plane. And the thing is, if I can recognize that very early in the production process, then I don't have to do the final steps in the production. I can already abort the production after the first 1 or 2 steps, which can actually save a lot of money. In this case, we talk about millions of euros. And here the task is to predict product quality as early as possible in the manufacturing process, so you can take the corrective actions needed to improve quality, or you can abort production and restart. And this, like I said, helps to save resources and money. Here's a depiction of how this steel industry process looks like. You first have the melted steel, and then after that it's turning into a solid material as a big block, and then there's several rolling mills to flatten the steel up to the final product that's thin enough to be used in a car or a plane. And you may have, for example, seven rolling steps, and if a problem already occurs after 1 or 2 steps, why should you be doing the other 5 steps? It's just a waste of energy and resources. So the idea is to prevent that from happening. Another scenario is you have a very large production plant, for example, in the chemical industry or in another manufacturing industry, and you have a lot of sensors all across the factory, and so you have a lot of data. But the question is everything okay? And then maybe you're overwhelmed. You have big data, you have too much data, you don't even see what's going on or where you should be looking because there's so much going on. So I'm not sure if you can see the little red arrow up there. It's indicating that maybe something little is happening there and you're not even aware of it, because too much data can also be overwhelming. So we did another project in the chemical industries with 3 companies from the petrochemical industry, BASF, INEOS, and PCK. And the task there is to detect critical situations as quickly as possible when they occur, or even better, predict them before they even happen so we can prevent them if possible. Or if they have already happened, provide assistance to fix them as quickly as possible. So the challenge here is that we have a lot of data from a variety of sources. So of course we have sensor data, all kinds of measurements, pressures, temperatures, what kind of ingredients we used. We have the parameters of the whole construction site, what machines are used, what is the configuration of the machines. We have sensor measurements from the laboratory. We have textual information, for example, the operators of the machines. Whenever something happens, they take a little note, manually written or typed, about what has happened. Everything was fine on my shift, or maybe there was a problem with too much pressure, we had to release pressure, and so on. And the goal is to integrate the data from all of these sources from the history of the plant to detect patterns of problematic issues and failures. For example, undesired emissions. When the pressure was too high, they had to release some steam, and that steam may have contained a chemical, so that's very undesirable from an environmental protection point of view. Or maybe they had to throw away parts of the production because the result wasn't good enough because there were some issues in between. And the goal is to predict these based on this mixed data. Another project, which is a bit more complex in scope, is not just predicting a single category or predicting a single numeric value. It was about predicting complete assembly plans for new product designs. So partners here, among others, were Daimler Trucks, in that case, a production unit for the truck engines, and Miele, which is a white goods manufacturer. They produce washing machines and dryers. And the task was, if they come up with a new product design, they automatically want to predict how long is it going to take to assemble this product. And then they also want to see what could be a possible plan to assemble the product. Like, what are the steps I have to do? Like, how do I have to compose the parts? Do I have to screw them, or do I have to glue them? Or what kind of connection do I have to use? And the challenge nowadays is in the automotive industry, in the white goods industries, and a lot of other industries, that the market is demanding more and more product variations in ever quicker cycles. But of course, as a manufacturing company, you have to go through certain steps. You have to design the product, then you have to plan the assembly, you have to set up the assembly line, and only then you can actually manufacture it. And now, in the classical approach, the product designer comes up with a design, gives it to the assembly planner takes a look and says, well, we can assemble that, but there's a problem. The person assembling that will have to reach from the back to tighten the screws. That's very difficult to do. It will take a lot of time. That means it will take a lot of time to produce this part, and it will be very expensive to assemble it. So why don't you do another design? So he gives the design back to the product designer, he changes the design, gives it back to the assembly planner, and they iterate until both of them are happy. The design is good, and the assembly is cost efficient. And instead of doing these iterations now, the idea is, if we have a system that can automatically predict the assembly time, the product designer doesn't even have to ask the assembly planner. He already knows how cost efficient or inefficient his design is, and he can iterate by himself in the design phase. And then also in the next step, when the assembly planner has to come up with the assembly plan, instead of starting from scratch from a white piece of paper, wouldn't it be good if he already had a recommendation how the assembly plan might look like? And that's exactly what we did in this project. So the goal was to use machine learning to automatically recommend assembly plans and to predict assembly times. Predicting the assembly time can be viewed as a regression problem. It's a numeric value I will have. Predicting the assembly plan is obviously a bit more challenging. A product design is something that describes a three-dimensional object composed of several components, composed of subcomponents, down to the smallest parts, to the smallest screw. And in case of a truck engine or a washing machine, that can be hundreds or even thousands of parts. So we have a 3D structure with thousands of parts that's somehow hierarchically organized. That's the input for the algorithm. The output is a sequence of steps, the assembly plan. So it's also a non-trivial output. And the problem is, if you look at the 3D structure, it's like a graph. And from a computer science point of view, you might think, well, let's find similar designs from the past so I can match it and come up with a similar assembly plan. The problem is, if you tackle the problem of finding the most similar graph, you have to tackle the problem of finding the most similar subgraphs, which is a so-called NP-complete problem. For those who are not theoretical computer scientists, what does it mean? It means there is no known efficient solution for that problem. In other words, if you want to use any state-of-the-art algorithm to solve the problem, you won't see the result in your lifetime. You have to wait too long. So solving it in the first intuitive approach doesn't even work. So we have to simplify the problem. I cannot go into all of the steps, but for those of you who are a little bit more into data science, I want to give you a few ideas. If you have ever worked in text analytics, for example, simple classification of texts, let's say emails into legitimate emails and advertising, like spam emails. That can be done automatically with 99.9% accuracy in classification accuracy. And that can be done without even really understanding the text. All the machine learning algorithms do in that case is they look at vectors of words occurring in the text, or phrases occurring in the text. And that's already sufficient to classify. So for that simple task of classifying, is it spam or legitimate email? Simple problem. I don't even need to understand the text. I just need to look at words and their frequencies. We took a similar approach here. Instead of understanding the 3D structure or having the algorithm understand the 3D structure, we looked at vectors of components, like which parts occurred, how frequently did they occur, what were the materials, what were the textual descriptions. For those, again, we use text vectors. So instead of using a complex 3D structure, we boiled it down to a very simple two-dimensional or one-dimensional vector. This simplifies the problem, but the question is, maybe it's good enough. Let's try. And so we tried that to find similar designs from the past and then use the assembly plans from these old designs to synthesize new plans. We did that by finding the components of the plans that occurred in most similar candidate plans and then merge that into a new plan. Okay, so this is just an idea that you can actually compose and decompose problems and algorithms. So we have a very complex problems. We simplified it. We used standard algorithms, in that case for clustering, to find similar groups of similar production plans and designs, and then classification to automatically predict what's the most similar group to assign a new plan to, and then we look at those plans to synthesize a new plan. So the goal was to predict this automatically for new designs, and we achieved that with quite a high accuracy, roughly 75% on terms of classification accuracy. I already described the challenges, so maybe let me give you an overview like it looks like. So we have on the left-hand side a representation which is supposed to be the designs of the products. It's a three-dimensional structure with components and subcomponents down to the smallest screw, some of them having textual descriptions, others having material properties attached to them. And then we used clustering to form similar groups. For example, the exhaust pipes are one group, but maybe the turbochargers are another group, or the oil containers are another group. And it doesn't make sense to compare assembly plans across component groups, but only within a component group. So we use clustering to automatically identify these groups. In a second stage, we use the classification learner to train the system to automatically detect for new component designs what kind of object they actually are. Are they an exhaust pipe? Are they a turbocharger? And so on. So the next stage for new products, they would automatically be classified to the appropriate group. Once we have these groups and we have this new design, we try to find all the groups that are most similar to that particular design, and out of those groups we take the most similar candidates and we use those to then come up with the most likely plan for assembly. We present that to the assembly planner, who then can say, yes, those steps I will take, but there's one step I wouldn't do, and I would instead do something else. So it's not a perfect solution, it's more like an 80% solution. But it already saves a lot of time for the assembly planner. So, what does this now achieve? Obviously, we have a very accurate prediction of what kind of component the designer has created. We have a comparatively accurate prediction of the assembly time, and we have the assembly plan candidate. This now allows to accelerate the whole process. The product designer doesn't have to iterate with the assembly planner. They can directly come up with their best design. The assembly planner is faster because he doesn't have to start from scratch. He can start with the 80% solution. That means overall the process of designing and planning the assembly for a new product becomes much faster and also much more cost efficient. So the company overall becomes more agile. They can have more variations of the products in shorter time at a lower cost. So it makes the company actually much more competitive. We have a lot of other industry projects. I don't want to mention all of them. There's one that we started this year. It's with the beer brewing industry as a representation for, in general, the process industry. Could be other food process industry or in general also biochemical industry, where the goal is to analyze the production process and to optimize it, to optimize the yield you can achieve with certain ingredients, to optimize the speed, have a higher throughput of the components, but still having a sufficient quality level. Again, predictive maintenance, avoiding failures of machines, predicting the quality of the resulting product, in this case the beer, for given ingredients, and in that sense also trying to optimize the mixture of ingredients. And there's a lot of other applications around that, for example, energy optimization. You have a lot of cooling systems, and the goal is to avoid peaks in energy consumption. So maybe you can change the timing of when you start certain cooling machines or pressure generating machines and so on. So, I want to give a few slides on what's behind all these applications. That's a platform called RapidMiner. It's an open source based software that we have developed. We started developing that software in the year 2000, and we started a company to support that development in 2007. It comes with different components. It's a visual interface to design data analysis processes. It has also a server that can help you to automate processes, for example, to repeatedly execute things, and also to use a scheduler to repeatedly do these things, to use web services so other systems can basically query the system, like given these parameters, what is the prediction for my desired problem? There is a marketplace, so third parties can develop extensions for the software. Universities, research institutes, or also other companies. The so-called RapidMiner Studio is the software that is used to visually design the data mining process. So each box represents a step. For example, import a data set from a database, from a text file, from sensor data, and so on. And then at some point you do the modeling, you do the predictions, and this can be automated later on. So coding is not necessary. You can visually design a data mining process. But if you want to code, we also seamlessly integrate other open source tools like Python, R, Octave, and so on. An open source software that has a good quality is like free beer. If you like it, you recommend it to your friends, and that leads to a high growth because people keep on recommending it. This is an overview of the user numbers of the software over the recent years. And you can see we started with quite small numbers, and now we have achieved more than 500,000 registered users in more than 150 countries worldwide. There's market overviews of what are the most frequently used tools in the data analytics space. The interesting thing is the top 3 tools, Python, RapidMiner, and R, are all 3 open source based. Python and R being programming languages, and RapidMiner being a more visually oriented data science workbench that integrates Python and R as well. There's also market analysts like Gartner and Forrester that compare data mining solutions, and also there we score quite well in the so-called leader quadrant. Also, customer feedback is very positive. We're ahead of other known solutions with regards to customer satisfaction. And a lot of reputed companies use our software. In the automotive industry, it's companies like BMW and Daimler. In the manufacturing industry, it's pharmaceuticals like Sanofi and many others. Thank you very much for your attention. Not sure if there's time for questions. I'm happy to answer, also afterwards in the breaks, if there's not enough time now. Thank you very much. Teşekkürler.